10%. So 0.5, 0.1. So 1 over 0.1 becomes 10. So if the rounds are independent. So that is the average number of times you try so that you hit not this one. So what is 1 minus P0? What is P0? P0 is that you are in 0 and you stay in 0. So what is 1 minus P0?
Change to turn to
Change in state.
Exactly, that you are in 0 and you change. You go somewhere else. Could be a state 1, 2, or whatever, but not 0. So from 0 you leave. So this is the probability that you leave. This is a try. The market switching tries to leave. It doesn't work. It stays.
So if P00 is large, then your chance of staying in that state is large, right?
Yes, but 0.955. 95%. So in this example, then this turns out to be 1 over 1 minus 0.9525, right? Let's calculate the number, and then so we will get something. And then try to calculate, or sort of understand what it is. So what does 21 mean? And it doesn't change this duration. The average number of days that you don't change the duration. Sorry, what did you say again? Can you repeat?
So expectation is equal to 1 over T. That means the average number of time that the value we change is 8, right?
That's right.
Yes. So what? So we overall.
So for the throwing dart, it's like you have to throw 21 times.
Exactly. Till you hit the target. And what is the target here? Leaving the state. So you have to, on average, try wait 21 days till you leave. In other words, 21 days on average you stay in 1, then you leave. That's the mean. So let's calculate this for the other machine. Right? So here we have from 1 to 0. So then, well, if I had P11, then I would have said 1 minus P11 and inverse. Well, but this is 1 minus P11. Because this is, you are at 1 and you leave. That's the probability of succeeding, leaving the state 1. So 1 over P10, which is 1 over 1 minus P11. In this case is 1 over 0.1096. Let's calculate it, roughly 9, right? Right, roughly 9. So let's see. So 9. Roughly 9. So when I'm in 1, then it takes me on average 21 days to equal. when I'm in 0, then 21 days I need, so that I leave 0 and go to 1. When I'm in 1, then it takes me roughly 9 days to be 0. Alright, so roughly twice of the times I'm in regime 0. Right? Well, sort of half of the times in all of the cycle, the data that we have, more or less like half. So 9 to 21. It's like 10, it's like 20. Right? So if I have the time, that's a big chunk, and 1/3 of the time, roughly, I'm in regime 1, 2/3 of the times I'm in regime 0. So I have 0 and 1. So that is some, what? And as I said, so that's sort of, that's a geometric random variable. And then can be used to interpret a little bit further with respect to these probabilities. These are the probabilities, they are quite actually that doesn't, so that's all right, that makes a lot of sense because P00 is 95 and P11 is 0.9. So the probability that you are in 1 and stay in 1 is 90% roughly, and the probability that you are in 0 and stay in 0 is 95. Because more often you stay in 0 than in 1. And that is also reflected in these average calculations. Right. Well, should you start plotting the results, maybe and compare them with the OLS over time, over all of the time period, to see then the verb graph. All right. Well, I mean, to simplify the matters, all right, then I will do sort of the probabilities. I will get the probabilities and then define some thresholds so that I say, okay, so if the probability is bigger than 70% for one regime, then I'm there. Otherwise, I'm somewhere else. All right, so that's sort of to simplify these matters. But let's get the regime probabilities. All right, so probability pros. And by probability. All right, so let's get the regimes. All right. And we can calculate the steady state probabilities and so on and so forth. Right? So here's what we have. So let's look at the results. So results that we not these. Just before I go on, let's say we look at the results. The results have parameters, are called params. Results params. So, well, I mean, there are the transition probabilities, and there are the constants, alpha 0, and alpha 1, and the 2, and then the coefficient of all of the variables that we have here. So, that is what we have. And then we can basically get them. Right? This is start with alpha 0. So that is the alpha in regime 1. And that will be results dot params. Well, that is 0, 1, 2. So that's in location 2. Alright, so I log of 2. Alright, so that is what I have. So that's alpha 0. I can get alpha 1, that is in the next one. Alright, and so on and so forth. So 2, 3, 4, 5, 6, 7. Alright, that's sort of what I have. So the structure is, so 2 and 3 are alphas. 4 and 5 are the kappa and betas. And 6, 7, 8, 9, and so on and so forth. Right, so I have all of them. And look at the sigmas also. So sigma in regime 1, regime 0, where alpha is a small, capital alpha is 0.5, is smaller than sigma variance in the regime where beta is high. So because when we let them to switch, all right? So here beta is higher, all right? So that's a more turbulent time. And then it's also reflected in the variance. Right? So there is much variance in the shocks, right, compared to the other regime. So that's sort of a less smooth, fine state. And then this is a state where the variance of the residuals are very high. So that is something which we also see. Right? So that's like the standard deviation is like 1.3 roughly, and then here it's 4, the standard deviation. Right. So we can like sort of keep in mind this and start plotting. Should I plot them all together? Maybe all of the coefficients, not just alpha. So let's estimate the sort of plot them all. Right? So when the number of the coefficients is 6. So there are 5 factors plus a constant, so there are 6. Right? And then the parameters, they also have names. So where we have the parameter names, where there is an intercept, which is the alpha, there is the market, alright. Then there's a small minus b. What was holding factors also. Alright, so these are the ones. I can just take it and put it here because I want to sort of track them and plot them neatly. Alright. So there are 6, so I need subplots 3 by 2, right? So that I can indeed plot them all. Right? So let's generate then a figure together with some axes. So here I will have the subplots. Number of rows is 3 and 2, right? And then I'm good to go. Right? Let's have the x to be shared x, or the x-axis to be the same across all of them. All right, so that sort of makes it a little nicer. Right? So, well, I mean, these axes that are generated, so you have worked with subplots before, potentially, yes. All right, so there will be, so this axis, the way we generated, will be some object, all right, which includes, say, 0, 0. So index 0, 0 will be the first axis. Then we have 0, 1. Then we have 1, 0. And so on and so forth. So that is what we have. That is how we should access them. Right? So that will be a 3 by 2 structure like that. So that's something I don't really like because I have one loop. So I need flatten. Make them flat so that they are from 0 to 5. So that this is the structure I need. So that will be.
Sorry, Professor, can I ask something? Maybe a bit naive, but like in this Farman factor, we have 5 factors.
Right.
Here the coefficient is 6, which including the alpha.
Alpha, yes.
The alpha is it related to the constant, the c then?
That's right.
Okay.
So that will be the constant in this revolution. Exactly. Very nice. So we have 5 experimental variables plus the constant, and they become 6. Very nice, thank you. So then I have the axes. Let's flatten them so that they are not 0, 0, 0, 1, 1, 0, but rather 0 to 5. So that will be easier. And now let's go plot. So I say for I in the range of non-coefficients. Okay. This is general, so you can indeed access them. Then I have a parameter at regime 0, which is resolved. Right. Dot params. Right. is first 0, then becomes 1. Then let's say we have an II, which is I plus 1. Right? So II becomes 1, 2, 3, 4, 5, 6. Right? So the parameters were also, if you remember, right? So let me show you the parameters again. Here they were. Right? So then we have 2 and next, 4 and next. Right? So that is 2 times 1 and 2 times 1 plus 1. Okay? So, or 2 times 2 becomes 4, 2 times 2 plus 1 would be 5, and so on and so forth. So I can read them all. Okay? That is why I define this II. So that will be 2 times II. Alright, so that's sort of what we have. And that is the one for regime 0. Okay? And then we do it for regime 1. That will be the next. And let's call this parameter. These are the parameters. Because I want to indeed plot. Alright? So but now we have to also remember that we are either in this or the other regime. So not always, I can't plot them all, because depending on which regime I am, then I have already either alpha 0 or alpha, depending on the regime. If I'm in regime 0, then I have alpha. And then there is times that I don't know what I'm on, or where I'm on. Then I have an average path. Alright? Well, there is an average parameter that I have. And then for that, then I need the probabilities. Probability that I'm in this regime or the other. So P0 at time t, and P1 at time t. There are 2 parameters of probabilities, right? So the average parameter will be then P0 at time t, so that's the probabilities of the average across time. These are pi's. Pi index t times say alpha 0 plus p to be regime 1, which is 1 minus that, times alpha 1. That becomes a simple expected value, or an average. So the average I will also calculate. So then for that, then I need the smooth probability, sort of the probabilities that, so that I can go and then calculate basically the quantities. Let's get the smooth probabilities, and they are easy to get, right? So they are safe. Let's call them, we need the smooth probabilities, smooth raw. They are equal to, and then I have the result, right? And then that includes the smooth marginal probabilities. When they are estimated, they are saved in this wrapper. Right? So the results indeed includes the smooth probabilities, and I'm using it. They are here. So if I have the smooth parameters, then the average parameter will be param 0, right, times the probability that I am in regime 0, right, times smooth props in regime 0, right, plus param 1, right, times the smooth props when I'm in regime 1. There are sort of 2 vectors of probabilities, and so you understand what I mean. So I'm calculating an average of the specific parameter. So now that I'm here, then I can start collecting essentially the data into a data frame. Let's call it DF parameter. That becomes easier to indeed collect things. Right? And so here then we have a data frame, and then let's its index be the smooth parameter index, smooth probabilities index. Well, that becomes easier to plot later. That's because we have the time index in this data frame, and plotting business will be easy. Right? now let's add the parameters. Alright. So df param. Alright. Then let's add maybe regime 0 parameter. Alright. So first let it be empty. So let it be empty. I will fool it like smooth props. Alright, 0 with none. Which field value we have? Let's say empty. Alright. So let me be empty smooth props.
Yes.
Well, let's maybe simply full of nuns first. Alright? So I do it because, well, I mean, later in the location, when I'm in regime 0 or regime 1, then I'm replacing the corresponding value. But then, well, the rest I will leave untouched as none. Because the nuns, well, will be there at a certain date, and they're empty, there will be nothing. So when you pass it to PLT plot, the matplotlib, then PLT, actually the matplotlib just leaves it empty and goes to the next, basically, point and so on and so forth. If you connect them all together, then you have to always also connect in which dates they are. Like this, that becomes a little bit easier to plot. You understood? Alright. So let's do this also for the others. Alright, so regime, say 1, and regime, well, we do average. Let's go to 0 or 1, I don't know which. Alright, so that's sort of what we do. Now let's just start plotting. Alright, so alright. Now, I mean, if I want to do plotting, then I have to know essentially where the probability of being in regime 0 or 1 is high. Alright? But let's then maybe after this, let's define some mask. Let's call it mask 0. Alright? And that will be, well, I mean, let's look at the smooth mask 0. That will be when the, well, we can pass it as a top of, so when the smooth props in regime 0 are bigger than or equal to 0.7. That's a number I make up. Right? Well, I mean, we are not for sure in regime 0 when the probabilities are bigger than 0.5. But that's high. I could use 0.8 or something. Right? But that's for the visualization's sake. So we see what is going on in our sample or sort of in our data. Alright? And then let's define another mask. Let's say mask 1. And I would say if the smooth probabilities here are smaller than or equal to 0.3, so the smaller one, so the probability of being, well, that will be a zero, true false. So the mask is true false, and you know that you can use masks of true false to extract data from data frames, right? So that is what I'm doing. Right? And if these, I mean, none of these actually happens, not this, not the other one, then let's say, well, we don't know what to do, so that will be an average. Right? So that will be the knot of the other masks. Mask 0 or mask 4. Okay? So if this is 0, well, that's an OR. So not an OR. So not this becomes not this and not that. Right? So you are in the middle. Yeah, clear? And this 0.7 and 0.3 I made up as a mistake, so there is no theoretical reason why. Just made it up. So I have these three masks. Alright, so now with these masks, then I can go and then do the plotting readings. Alright. Like so. So here then I would say, so when I'm in this DF param, alright, then I go in the locations var mask 0 is true, and this reg 0 I set to param 0. And then I do for the other one. So here I have mask 1. And then I have the average. So I call it ABG. And then the variable that we have is 0 or 1, we don't know which. And that will be the average param. Average ABG param, but not everywhere. We just do it in wherever this mask is true. So wherever it is not true, then it's remain as not none. Yeah? Well, I mean, potentially you have done this all in your Python class, but then now I use them. Right? So that's sort of the usage of those. So here, then we are good to go. So then we have all of these. Now that we have them, then we can go and plot. Let's pick one of these axes. So that will be axis, say I. And then start plot. So PLT of BF param. So we put reg 0. So that will be the one that is in regime 1. Alright. Let's add a marker. So let's say it's an O. So that's a dot. Let's not add any line. So the line is done. Is none. I just don't want any lines, otherwise it will be very ugly and we will not see. Let's add a label, which is regime 0. And then let's add a color. Let's say orange. It's a very long block. Alright, so that is what we have. So that is the first one. Now, let's do the others. Let's go to regime 1. We'll change the label to 1. Let's have this green, so that somehow we distinguish it from the others. And let's have the average as blue. And that is regime average. And 0, 1. And then now we need the OLS, just one OLS. So here we say, what do we need? We need a horizontal line on the X, where we had, what did we call it? OLS model. So that will be the params. So let's also have the param. And then we go in the location I. That will be 0, 1, 2, 3. So all of the params, there are 6, and all of them are big. So I don't need a marker. So let's have the line style to be dash dot. The label is the OLS. And then let them make the color. Right? Well, I mean, then let's make it a little bit nicer. So we say x dot, now let's add a title. We set the title to, what do I call them? So the names, well, param names. Param name. At location I. Right. X dot greet. Let it turn on. So that we have greet, and then we can compare them. And then, well, I mean, let's add the otherwise no, otherwise it's no. Alright, then we are good. DLT, let's say we have a hard layout. DLT will show. Yeah. Well, and that was sort of playing with around with it. Functions and so on. So the class runs till 4, right? And that is 320.
22.
It's so fast. Okay, so did you run it? And does it work for you? I don't know if it works for me. So this is this and parameters and it's too small in the other. And let's run that over. Item. Multiply or multiply two. Hurrah. No, that is a nice graph. Well, maybe we could make these markers a little smaller. Alright. Or we can explicitly make that, or that is the sum plot, we can fix the big size, right? So that will be doing the same. Let's say big size is, I don't know, let's say 15 and 10. Oh, that's better. Okay. Well, you don't have to drag.
Sorry.
I just set it to 15 and 10. Let me show you the code, and afterwards I will come and talk about it. Okay. Because we could add also the confidence band and so on and so forth, and make it nicer and so on. So. So that's the main loop. Can you read it? Maybe you can check and then I can also come to your laptops. Because I learned from your mistakes. When you program, I learned from mine and I learned from the others.
So,
You don't have, there is nothing that I could learn from you.
it just copied.
Fig size equal to, and now parentheses is open and closed, and pass it as a topic, 15, 10. Now, hopefully video. Struggling. have the loans. You're fine. Oh, I think that you know. Pie chart. That's the, I use, when I do serious programming, I use pie chart. Well, I mean, I do a lot of programming with generate videos. And that is, I don't use this, I use pie chart as a stronger, or sort of I feel more comfortable. So, and because you can do a lot of the stuff with Python, right? So, or, well, I mean, now and then, just for the fun, I write some apps for the fun. Alright, so apps you can install on your laptops. This is my hobby. And they also use PyCharm as well. You could also plot the probabilities, just to see them. But we have them, that's actually no big deal, right? We could add another layer here, say 4 by 2, and merge them, and then have this one probabilities. So that- Min, how are you doing? Good. Quiet? Rate 1 and rate average as a code. There's a value here. It's also full. Focus on the index, so you have everything like I have. So then here we have df param log. This is probably the issue. welcome for nothing. Absolutely different. Marginal probability. But let me just talk about the graphs, okay? So let's make it a bit bigger. We'll of course post the line so that you can check which part you have missed or not, so on and so forth. This is the plot. Well, that's the alpha, right? And the alpha of OLS is small. That's the dashed line. The dashed red line is the OLS system. Then there is a green. That's the regime 0. And there is an orange. That's regime 1. Yes. And these dots that you have, they are blue. They are the averages. All right. Well, I mean, now let's look at them. Let's look at the alpha. So cap M alpha from OLS is actually smaller than both. It's smaller than orange, which is the regime 1, so that's sort of the smaller one, and then the smaller than the other. So sort of that is what we see essentially here. But cap M alpha from OLS actually is significant. So the standard deviation is estimated so small that it turns out to be significant. Maybe we should have gone and redone this using, say, interest elasticity models and then see what happens to the coefficient. We can't really do that. That's sort of what we see. So, and what we see is that this market switching model and the CAPM, well, I mean, apart from, say, this graph, the alpha, and this one, it looks like that the OLS gets somewhere near the average of them, so it's in the middle. The red line is in the between of the two. Right? So sort of, well, apart from the finite slope and that guy, then it looks like that the averages that we have is very close to this. So this one is between the two. Here is much below, so it's right below this. And then there is also very below for the alpha. Right. So this may, to me, it may indicate that this CAPM alpha is a non-linear thing. Right? So that's a non-linear function of time, potentially. All right? So I wouldn't actually rely on the CAPM alpha of the OLS. All right? So if it was sort of more or less in the middle, that I have a high regime, a low regime, and then you will just get some average, because it is indeed an average. Right? Or let's just capture something which is in the middle. It gives you a hyperplane or sort of a regression, which is in the middle of all of the data. It should be. Right? So if I have two regimes that gets me a higher and a lower, indeed beta, then it may well be that, well, the OLS, which is average, should be in the middle. It doesn't look like. So maybe that this parameter that we have here, or this high minus low, has some nonlinear effects. Right? Maybe I should include this power 2, or I don't know, some interactions with other variables, and then make my regression better. All right? But that's sort of, this is a feeling. This is not sort of what you should do, but I'm just telling you the stories I get out of this. Right? Okay. And then let's look at the maybe S and B, right? So the small minus big. So we see that in regime 1, that's the blue one. All right. So there the cap M beta is bigger. So cap M beta, the green is up there. But here this coefficient is the smaller. Right? So look, these two are reversed. Orange, green, and there we have green, orange. So kappa beta, when it is green, then it means we are in the regime where kappa beta was 1. So this is the time where things are more risky, higher kappa. And the orange one is where we have the kappa beta low, around 0.55. So that is where we have less risk exposure. All right. So, and that's sort of reflected here too. So here we see that when we are in the situation where kappa beta is higher, so you have a higher risk exposure, then the effect of the small minus big is much greater. So if it's bigger compared to the case where kappa beta is small, which makes sense, right? Because this is a small minus big. This is the bad performer, or sort of the small basic companies, and minus the big one. And that also happens to be reversed for high minus low too. Right? So the high performers minus the low performers. Right? So when this distance is very big, range is large, and we are in regime 1, then the effect is slightly bigger, not much. That's minus 97. This is 125. Alright. So 1.125. So the numbers are not too far away, but still we see a decrease. But for the other variables which are also taking care of the turbulence, which is in the market, then the reverse you also see the coefficients are negative, right? And then they become stronger when beta is small. Right? Now let's look at the orange, green, and blue. Right? There are times when you are sort of the probability that you are in the higher regime is sort of big, right? Bigger than 0.5. Then we are here. Right? So this looks like to be around the end of the sample. I don't really see the dates. And there. So, but that's 22. Alright, so let's just start 22. So when 22 starts, then there is a long period of time where we are not in regime 0. In regime 0, yes. Orange is regime 0. There is some time period where we are not in regime 0 for all of them, of course, right? So you see that there is an area where this is empty and this is the green, which is full. Right? Which also may be sort of related to some political issues that happened during the time, right? When did Trump came? When did he come? 22, roughly. Right, so I don't know, when was it, sort of? It's like 2 years, a bit more than 2 years that he's around. 22, right? Right. So it could be essentially that time. So where one didn't know, okay, so there came all these embargoes, wars on tariffs, and so on and so forth. So markets reacted to it, so we were in a more turbulent time. So NVIDIA, so this is what NVIDIA is. indeed, when more was in regime where kappa and beta is higher than in the regime where kappa and beta was low. And so on and so forth. You can just go on and make up your own mind of what happened then. But what is interesting is that we didn't include anything about Crump here. Alright? But it seems like that this results in line with what happened in real life. So these probability models indeed capable of capturing not everything that happened, but something, alright, that could have happened in real life. So this was Markov switching models, a bit of theory, and then application. They're also on the slides, they're also in the book, but here there is less. In this book there is less theory, but there are more applications. In this one is the same. Well, he developed also a lot of models that we learned to describe. So, yeah, exactly. So, well, I mean, here there is more theory. Right? That's in the very end of this, basically. But in this last minutes that we have, then I will look at the slides. There are some more models. I will not implement them, but I will tell you what they are. Okay? And then we will be more or less out of the Markov switching, and tomorrow I can do investment. But in the beginning, there is some slides about the structural changes. I just moved over them because we know that if you have a structural break, then you bring in a dummy, and then you take care of it. So that is something I didn't do. Right? So these are the Markov properties, very briefly, the probabilities, and so on and so forth, which I also told you. There is an application of the purchasing power parity. Right? Well, you can read it. That's a very nice one. All right. That's Hansen. That should be a nice paper to read for you. And then there are also some other models which I wish to use, and one can do forecasting, but they are weak, as I said, with forecasting, so I mentioned that. There is another application, right? So to the exchange rates, which you please also read for yourself, but I want to talk about threshold autoregressive models. Right? So this is the last part that we have here. We call them TAR. T for threshold, AR for the autoregression. And threshold actually models have sort of a structural break, but here there is also a state variable. Right? The state variable is not 0, 1, but is rather something, right? That some exogenous maybe variable. When this is lower than the threshold or higher than the threshold, then you will have this or the other regression. But it's like a structural break if you wish. Right? But it's a structural break actually where this ST can vary. Sometimes it may be above, sometimes it may be below some threshold. But the idea actually comes from some regulation that previously one had with exchange rates. Right? And when the exchange rates were too high, then some actions were taken. One does something. Right? So when they are too high, or when they are too low, then you do something. Right? You don't do it normally. If the exchange rates are okay, then you don't do anything. Just let the markets go. But if they become too high, if your local currency depreciates a lot, then you need to implement something. Right? So some policies. And that will make the dynamic, that will affect the dynamics. So exogenous, it's not so much exogenous, because when you look at the exchange rates or some variables that you are sort of analyzing, if it is somehow high or low, then you do something. Or maybe some other variable, I don't care what. Right? So these are variables or sort of ones, we call them threshold ones. Top. Right? So, well, I mean that the switch between the regimes is governed by some observed variables. previously, in the micro switching models, we didn't know how do we switch from one regime to the other. That was the stochastic first. It still was a stochastic. But here it is not. Well, sort of it is. It depends on S. We observe S. It is higher or lower than we sort of are in this branch or the other. Well, we're going to be warm and then estimate this one. I just want that you know these and then the threshold models. But then, so remember the exchange rate. So let's say this is the exchange rate or sort of some variable that you analyze. And then when it is too high or too low, then you're sort of in this branch or the other. Right? Well, so to speak, the S that T minus, K is lag. For example, let's say today something happens and after 1 week, you switch between the sort of regimes. That's what the lag K that we have. But somehow, sometimes you may want to indeed replace this SK with, well, not some other observed variable, but rather Y. Alright? Y is something that you have. So 10 periods back, it was some level, okay, you say 10. Then if it was 10 periods back too high, then you switch. Right? Well, that's a parameter that you can choose, of course, using AIC, BIC, or model selections. So you have the data. And these are models which are like them because they excite themselves by themselves. So they sort of decide whether we should go to this branch or the other one, not using an exogenous variable, but rather the variable that we have and had and we want to analyze. And as such, then they are called the self-exciting threshold autoregressive models, for short setup. So that's sort of these models that we have. Well, I mean, that's sort of, well, again, so in here, then when you switch, then you know that you are there. Right? In Markov models, we didn't know. There was always a probability attached, that whether we are in this regime or to the other. These are a little bit simpler. And whenever we have a rule that tells us under what conditions you switch, then you may handle. If you don't know the rule, don't have the information, then you may go with the other ones. Right? If you know that there are structural breaks, and you don't know when did they happen, then you can use Markov models. If you have some rule, then you can indeed use those. Right? Well, they are tricky to estimate. They're a little problematic. They're not so often used. Right? I think knowing them, knowing if somebody talks about setup or tar, then you know what models are meant with respect to this. Right? There are some again examples which are there for you to read. We will not go through them. Right? So they are forecasting the stuff just to say so how good they are, do they actually work, and so on and so forth. Well, I mean, here I have this set up with one threshold, but you can have more. Right? For example, there you can have, say, so a band, you feed sort of the data, and then data say, are here, when they hit here, then you go in one regime, and then you come back, to the regime you were, and then you go to another. Right? So that's sort of 1, 2, 3. So you have 2 thresholds. So a band, or more. That's indeed possible. That's an example, which I said I don't want to go through. I think Markov's are good. And I'm done with this section. Well, today I will add some exercises online, for you just to go through. I will formulate this derivation that I had with normal, because I think when I just did it with mu, I will let you do it with respect to sigma and p. So there are 2 other basically parameters. I will update it so that you can update your assignment. And well, the previous assignment is also nice that I added on Friday, that's correct. One is with the value at risk, so if some of you are interested in risk management, and knowing what value at risk is and how we could quantify it using Garch models or asymmetric Garch would be interesting, so that is what I have. Here I will add these little stuff. So the integrations I did here with this equation, I will also add as an output. I will add it so that you have it. I'm not going to do it with respect not to mu, but rather sigma. One and alright. So well, let's actually look at what we have. Alright. And so that is actually pretty much a bit of theory, a bit of stuff. What I want to do next, so that will be tomorrow on, is on MPT. Alright. So the modern portfolio theory. So portfolio allocation you have done, I suppose, in some other courses, theoretically. So I will review them, ask you some questions so that I know who am I talking to or what you have learned before. And then I will go put together a portfolio. Yes, so do portfolio optimization using data. That will may take, say, 1 or 2 days, I don't know, depending on how many exercises we do. And then we will be essentially good. Alright. Enjoy your evening.
Thank you so much.
If you have questions, I'm here. I'm not